In this revision session, I will be going through the questions proposed for your next quiz. I will solve these questions. So let's begin. The table contains information about 4 samples of different monoprotic acids with the general formula HA. Now, before you read the question, just analyze what you have. I have samples, the volume is not important, the concentration is important, they are all at the same concentration. However, the pH at this point is going to indicate which one is stronger than which, because an acid, when it ionizes, it's all about how much H plus it forms. So the more it forms H plus, the more it is strong, the stronger it is. And when we have a lot of H plus, it's gonna lower, the pH will be lower. This one has the highest concentration of H plus, and this one has the lowest produced the lowest concentration of H plus, which means among all these acids, the one that having the same concentration, this is the weakest because it didn't ionize so much to produce H plus, and that's the strongest. Now, having a pH of 1 is a really strong acid. Now, 2 and 4 seems to be equally or the same acid. So let's begin with the first question. Which particle drawing best represents a portion of sample 1? Remember, sample 1, that's the highest, that's the strongest, having a very low pH. I'm gonna choose among those the one that ionized the most. And when I look at the key given to me, so I'm gonna see in which diagram I have the most broken molecules, the one that separated. So this one, H3O plus, and as you can see, HA unionized, so definitely not this one. Here, all of the HA ionized. This one shows a strong acid. This one just shows the acid unionized, and this one shows an acid ionized partially. So if I want to compare A and D, D is stronger than A. However, B is the strongest among them. And here they are looking for sample 1 that we qualified it as the strongest one. So the answer is A. A could be the weakest, which is sample 3, and D could be 2 or 4. Next question. Which statement correctly explains why the pH value of sample 3 is the greatest? The greatest means the weakest. And when I have a weak acid, it means the least ionized, because it's a weak acid, it cannot ionize. The one that produced the least amount of H plus concentration. So it has the smallest value of H3O plus. That's a valid reason. Of course, in this case, no, B is wrong. When it has the weakest conjugate base, to have the weakest conjugate base, it means it's the strongest acid. Yani C would be matching if they asked me why this is the strongest acid. And they're not talking about the strongest acid. So the choice is A. Which sample has the smallest value of Ka? Smallest value of Ka. The weaker the acid, the smaller the Ka. Ka is the dissociation, it's the ionization degree. So the larger the Ka, it shows that the acid is strong, but the more weak The weaker the Ka or the smaller value of Ka shows that this acid is barely ionizing. So we're gonna go with the weakest acid. And the weakest acid was sample 3. Next question. A student pours a 10 milliliter sample of a solution containing an acid. Here's the pKa and NaC2H3O2 into a test tube. Here's the conjugate base. How do I know? I just compare them. Look, there's the H that is donated, and this is the conjugate without that H. So we're looking at HC2H3O2, and we're looking at C2H3O2, its own conjugate base. So our student pours these two, the acid and its conjugate base into a test tube. The student adds a few drops of bromocrazole green, that's an indicator, to the test tube, and it observes a yellow color. You don't have to know the colors, but you know, here's green. So definitely with the color change, there's either the solution is acidic or basic. Now, which indicates that the pH of the solution is 3.8. So the pH is on the acid side. Based on this result, which of the following is true about the relative concentrations of these two substances in the original solution? That's a very simple question. You just have to read carefully. It's acidic, that's more. So the answer is A. Moves HCN plus H2O, H3O plus, and Cn minus. So as you can see, that's a weak acid because it partially ionized. Also, the value of Ka shows that this is a weak acid. The equilibrium reaction shown above represents the partial ionization of the weak acid. Okay, so they gave us a certain molarity of HCN with a pH of 4.9, almost 5. So again, this clarifies that this is a weak acid. And then if 0.049 grams of its own conjugate, Cn minus, is added to the solution, which of the following explains how and why the pH of the solution change? So what we have here is an acid, HCN, with a certain molarity, and we added to it some Cn minus. Now, you need to know that this acid, or if I look at this equation, some Cn minus was added to the equilibrium. Okay? So, what happens? Cn minus is basic. I am adding it to an acid which is weak. Fine. Now, this acid is going to become less acidic. The pH is going to increase because you added a slight amount of base. Also, if I look at it from the perspective of Le Chatelier principle, adding Cn minus to the equilibrium will shift the equilibrium a bit backward. Okay? So this is going to affect the acidity because H3O plus is going to be less. So less acid, or the pH is going to increase. So here they're asking what's the pH of the solution. The pH will be higher. So I'm gonna cancel the choices where they say the pH will be lower. So you have an acid, you added a bit of base on it. So definitely the pH is gonna go higher. Now let's see which reason they're talking about. Cn minus is a strong base. It's not a strong base. It is a weak base. They added a slight amount. However, Cn minus will disrupt the equilibrium. See here, they're talking about Le Chatelier principle. So the equilibrium is going to be disrupted. It's going to go backward, resulting in an increased production of HCN, true, and less H3O plus in the equilibrium. Less H3O plus means a higher pH. Let's continue. Based on the Bronsted-Lowry theory of acid and bases, which of the following species can act as both conjugate acid and conjugate base? They are talking about the amphoteric substances, the substance that can accept a proton, also it can donate a proton. So you must select the substance that can have one more or have one less. This one doesn't have an H plus to donate it, so it cannot be the answer. This one, it can donate H plus, but it cannot accept. I'm not gonna have H4O2 plus. So not an amphoteric. Same thing over here. We can have an H3, but we don't have an H5 plus 2. The only one is this one. HS minus. If it donates, if it's a donor, it's gonna be 2 minus. And if it takes an H plus from another substance, it's gonna be H2S. So if it's a donor, if it's acting as a base, I can remove an H plus from it. If it's acting as an if it's acting as an acid, I'm gonna remove an H plus from it to obtain S2 minus. If it is acting as a base, it's going to accept a proton and gives H2S. Now, next question. The equilibrium for the reaction between a weak base, look at the N in it, and water is represented by the equation below. The table shows the pH of 3 solutions of a derivative of nitrogen. It's a base. Okay, anything derivative of ammonia is a base. So here's the base, here's the production of OH minus, this is the conjugate acid, and this shows clearly that this is a weak base. Now, as the concentration of this base increase, the pH is increasing. Of course, if the concentration of this one increases, I'm gonna get more OH minus because I have more amount of a base. Yes, it's gonna ionize a little bit, weak base, but still the production of OH minus will be higher. So based on the information given, which of the following is true? Solution with higher concentration has a higher pOH. Pause. Higher pOH means a lower pH. No, here we said it has a higher pH. So it's gonna have a higher pH or higher OH minus concentration in case they mentioned this, or a lower pOH. These are the keywords I'm looking for. So it's not A. Solution with a higher concentration of this base have a higher pOH. No, we need to choose a lower pOH. Solution with a higher concentration has a higher pH. Okay, I'm gonna continue. Because to reach equilibrium, to reach equilibrium, a smaller amount of the conjugate acid is produced. A smaller amount. We said that the reaction is going in this way. It's giving me more of this. The solution with a higher concentration will have a higher pH, yes, because to reach equilibrium, more OH minus is produced. Next question. I have an acid, an organic acid. Look, it has COOH, and this is the acidic proton in it. I have a base, Na. I'm not interested about it. I'm interested about OH minus. I'll get C6H5CO minus and H2, which identifies the conjugate acid-base pair in the reaction above. These, they don't get along. Here, that's not an acid. These are conjugates, but it's not an acid. It's a base. So that's the best answer. Sometimes in the AP questions, the questions are very simple. It doesn't need a lot of thinking. Now, when a 0.64 gram of calcium carbide is added to 100 milliliter water and a calorimeter, the solution reacts with water as represented by the equation. So look at the equation. That's the powder that we added to water. We dissolved it in water and it gave me calcium hydroxide. Now this is a base, but so far it's solid. It did not dissolve yet. At the completion of the reaction, the pH of the product mixture is showing base. Okay, which means the basicity of this solution is gonna come from this one. Now, there's something about this solid, maybe not all of it dissolved. Which of the following can be concluded from this solution? CaOH minus, CaOH2 is slightly soluble. Yes. Proton donor, no, it's not an acid, no, and no, the final temperature remains the same. No, this reaction, now this is not in our lesson, but however, this reaction is exothermic. And when the reaction is exothermic, the temperature indicated will be higher. So the only thing shows that this insoluble compound is probably slightly soluble, showing that giving the basic feature to this solution. Next, HClO, that's a weak acid, ionizes to produce a conjugate base. Okay, so also the Ka shows that this is a weak acid. The acid ionization equilibrium is shown above. Aqueous solution of this acid has a pH about 4. It's a weak again. For solution with an initial concentration, let's pause here. They started with a 0.1. So at a 0.1 molarity, the pH was 4.2. Now when they increased the concentration, is allowed to reach equilibrium at the same temperature. Which of the following correctly predicts pH and why? So the thing is, this is a weak acid. pH is related to how much H3O plus I have. Now since the quantity of HClO increased, so comparing between the two, definitely this one is gonna have more H3O plus. I'm not talking about the percent of how it's gonna ionize or the strength. No, it's simply because the quantity is more. No matter how much H3O plus, the same percentage of H3O plus is gonna be ionized compared to the previous one, except that the amount that we started with is more. So we're gonna have a less pH, not because the acid became stronger, it's because the quantity we started with is more. So the pH is gonna be lower, more H3O plus. The pH is gonna be lower. Okay, so here are two choices telling me that the pH are gonna be lower because increasing the concentration of the weak acid will give me more H3O plus. That's what I said. The pH, let's read the other option, because Ka is inversely proportional. No, here we did not change the strength of the acid. The Ka is still the same even with this concentration. It's just the starting amount is more. So the answer is C. HCl and H2O, that's a strong acid, look, fully ionized. For the dissociation of HCl in water represented above, which of the following pair includes Bronsted-Lowry bases? Which of the following pairs include the Bronsted-Lowry bases? So, HCl base. So they're not looking at a Bronsted-Lowry pair. They are not looking at a Bronsted-Lowry pair. They are simply looking at the base. Acid, base, conjugate acid, conjugate base. So base, base. It's D. Read carefully the question. Now, again, another compound is acidic. That's the acidic H. The structure of halo acetic acid. Okay, so an acid containing a halogen, either FClBr or I, as shown above in the dissociation constant and molar masses are listed above. So let's study the table. So when there is F in it, the Ka 2.57 times 10 to the power negative 3. When there is Cl, in the periodic table, the order is F, Cl, Br, and I. Okay? So when they are changing the halogen, it's becoming, you see, Ka is decreasing. So as I'm adding those, Ka is less, or I can understand from this, the acid is becoming weaker. So the acid is becoming weaker. So the addition of this halogen is making the acid weaker. Of course, if the acid is weaker, if we talk about pKa and Ka logarithmic function, they're inversely proportional. Fine, so let's see what's the question about. An aqueous solution contains small but equal concentrations of both chloroacetic and fluoro. So they are just comparing the first two. Which statement comparing the percent ionization of the two? Percent ionization, so directly think about who's stronger, who's weaker. So as I said, by changing from F to Cl to Br, the acid is becoming weaker. So chloroacetic acid is weaker than fluoroacetic acid, or is going to be less ionized. So the percent ionization of chloro is less. That's it. Cannot be compared. So the answer is simply B. Moving on, I have a weak acid over here, ionizing. Okay, let's compare the table before reading the question. As the acid concentration is decreasing, or we're getting a dilution, decreasing, I don't want to say dilution, it's decreasing. So less starting amount of acid. Okay? Now, this is a weak acid. Now, we are not changing the strength of the acid to ionize more or less. We are simply changing the quantity. When an acid barely ionizes, the portion ionized compared to the initial volume, to the initial amount, is small. But when you are decreasing the starting amount, this small ionized portion is gonna become more important. Pause the video and hear again what I said. So because the acid quantity is now even less, the portion ionized compared to the starting quantity is more significant. It's not because the acid became weaker. The quantity is less, but when I compare a less quantity, the small amount that ionized became more significant. So that's why when we dilute an acid, the percent ionization is gonna decrease, not because the strength increased, no, because the acid quantity became less. So the quantity that's going to ionize compared to the original one became more significant. And the explanation to this is the concentration of H3O+. As I'm having less amount of acid, the amount of H3O plus produced is less because I have less quantity. So less is gonna less acid will produce. Less H3O plus will be produced. So the equilibrium for the acid ionization is represented by the equation above, and the table gives the percent ionization at different initial concentrations of the weak acid. Based on the information, which of the following is true for a 0.125 molar concentration? So they are adding this one. They are talking about a 0.125 molarity. Okay, it will have, it has a higher percent ionization. They are comparing it, wait, let me see, based on, and a lower pH than, so it has a higher percent ionization, okay, a lower, no, so let me put this, higher percent ionization, lower H3O plus. If I go like this, it's gonna be higher pH, and it's gonna be lower pOH. So these are the words we are looking for. Okay, so and here lower concentration. Okay, so this one is wrong. It has a higher percent ionization, okay, a lower H3O plus. It has a higher percent ionization, okay. It has a lower H3O plus, okay, and a higher pOH. No, that's wrong. Okay, it has a lower, okay, here they changed the concentration, so they are now comparing it to this one. So it has a lower percent ionization than this one, yes. A higher H3O plus, yes. A higher pOH, yes, because we're talking about, we're comparing now these two, yes, than this concentration. So my advice to you, when you look at a table, analyze the table and write the key points. And just AP questions are all about how do you read the question. So the answer is C. So as long as you write those here, finding the answer will be looking for those keywords and seeing which one they are comparing. Next, moving on. This is the autoionization of water. As it shows, it's an endothermic process. The endothermic autoionization of pure water, neutral, is represented by the equation shown above. The pH of water is measured to be 7 at 25. Of course, the pH is going to change if the temperature changed. Which of the following statement best explains these observations? As long as we are talking about pure water, the ionization or the water is always neutral. Neutrality is always when these concentrations are equal. Now, let's see which statement is correct. At higher temperature, water dissociates less. If this is higher temperature, it means plus delta H over here. So when the temperature increase, the autoionization equilibrium is going to shift forward, dissociating more. So here's the answer. Here's the answer. And that's why the pH, this, never compare these at higher, compare the Ka dissociation. So don't let those values confuse you. So the answer is D. Moving on, ammonia and water, ammonium and hydroxide ion, that's basic. This is a weak base that reacts with water according to the chemical equilibrium represented above. The table provides some information for two ammonia solutions of different concentrations at 25 degrees Celsius. Which of the following is true about the more concentrated ammonia and why? So let's see. When I used a more concentration, we obtained more ammonium. Of course, the starting amount is more. So the amount of NH4 plus produced is going to be more significant. Fine. Now, the concentration of OH minus at equilibrium, usually they are equal. So it's going to be 2.3 times 10 to the power negative 3. And the pOH, if I do minus log of this value, I'm going to get the pOH. So if that makes you comfortable, you can calculate it. So minus log of 2.3 times 10 negative 3 is going to be 2. Okay, so slightly less. So let's look at the answer that says pOH is slightly less than 2.7. Okay, we are looking at options A and C. So OH minus is 3. Wait, no, not 3.2, it's 2.3. See, silly answers. So that's the answer. KW. KW is always the concentration of both. It's correct. Okay, based on the information, which of the following is true for pure water at 7? It's not the concentration equal to 7 molar. No, that's KW. pH is 10 to the power. No, it is choice. We cannot take this as a, no, that's wrong. pH is minus log H plus, or H plus is 10 to the power negative 7, or negative pH. Now, since pH here is 7. So this is confusing. Be careful. So that's the correct answer. Ammonium. Okay, here's a reaction showing you. So NH4 plus is added to a base or mixed. The reaction represented above by the equation occurs and a strong smell of ammonia is observed. Okay, of course, from the arrow here, I know that there is a production of ammonia. So based on this information, which of the statement is true? So NH4 plus acts as a base. No, this is an acid, this is a base, this is a conjugate base, this is a conjugate acid. NH4 plus is a stronger acid than H2O. Yes, look at the arrow. It's only one side. They are trying to tell you that this reaction moves forward, and it's when the reaction always moves in the direction from stronger to weaker. So as a base, this is stronger than this base. As an acid, this is stronger than this acid. So this answer is correct. NH3 is a stronger base. No. And NH4 minus, 4 plus and Cl minus are pairs. No. Next, which of the following pairs of mathematical expressions can be used to correctly calculate pH and pOH of 0.0015 molar of KOH? KOH is a strong base. So KOH is going to strongly ionize, fully ionize, producing K plus and OH minus. So the concentration of KOH is going to fully produce the same amount of OH minus. So we want to calculate pH and pOH. So if I want the pH and pOH, I'm gonna start from OH minus. Since I have the concentration of OH minus, I can first calculate the pOH. So the pOH is gonna be minus log of this concentration. Now it's gonna give me a value. The AP questions, they will never ask for the answer. So after you get the answer of this equation, you're gonna calculate pH by using the formula of pH plus pOH equal 14. So if I put this value over here, I'm gonna get pH plus minus, so minus log 0.0015 is going to be equal to 14. Now in the question they are asking only for pH, so I'm going to move all this quantity in here. So pH is going to be 14 plus log 15. Okay, so here's the answer. So you just have to look for the answer. So plus log, and here we go. Number 19, which of the following statements about the pH of 0.0 molarity of a strong acid is correct? So pH is, do your calculations. This is a strong acid, it's gonna fully ionize. So the H plus produced is gonna be equal to this concentration. So minus log H plus is gonna be 2. So pH is 2 because the H plus is 1, not 2. Here is the answer. Moving on, which of the following is the correct mathematical expression to use to calculate pH of a 0.1 molarity of a strong base? Be careful. This strong base, when it ionizes, it's going to give me 2 OH minus. So if I have here 0.10 molar, here I have 2 point this concentration. So it's equal to 0.220 molar. So having an OH minus, I can first calculate the pOH. So the pOH is minus log OH minus log 0.20. Okay, and then they are asking for pH. pH equal 14 minus the pOH, which means 14 minus log. So I'm gonna write, instead of the pOH, I'm gonna put the value of pOH. So minus and minus, that's a plus. And here 0.20. Question 21. Which of the following gives the best estimate for a concentration, a small concentration of a strong acid? Okay, so here, that's a strong acid. So I'm gonna get, it's gonna fully ionize to obtain the same amount of H plus and ClO4 minus. So they want to calculate pH. So you find the pH minus log of this value equals 5. Here we go. Here's the answer. It's a strong acid. The value of Kw at higher concentrations, at higher temperatures increases. Fine. So the pure pH of water at that point is how much? To calculate this, we always know in pure water, OH minus is always equal to H3O plus. So Kw is gonna be H3O plus squared or OH minus squared. So you just have to, if I want H plus, I will say, I'm gonna use this one. So squared. So the H3O plus, which is equal to the concentration of OH minus, is square root of Kw. So square root of this value will give me H3O plus. So I'm gonna do it. Square root of 3.4 times 10 negative 14. Here's the answer. And then minus log that answer to find the pH, 6.8. So once you get the value of H3O plus, you're going to say minus log the calculated value of H3O plus. H2O, autoionization of water, now at 55 degrees Celsius. It's even higher than the previous question. So pure water ionizes as shown in the equation above. Based on this information, which of the following is correct? The autoionization of pure water favors the formation of products. As explained, when temperature increases, this is an endothermic reaction. More H3O plus and OH minus are produced. So favors the product. Same amount, no. So let's see here, they're doing calculation just like what I did over here. This is the formula I used in the previous question. I found H3O plus by doing its square root of Kw. Then I did minus log the answer to find the pH. Be careful here, they're saying Kw without the square root. So C is the correct answer. Which of the following gives the best estimate of pH of a strong base? So again, when this base ionize, is gonna give me 2 OH minus. So the concentration that you have here is gonna be doubled over here. They want the pH. So having the concentration of OH minus, you first find POH minus log of this value 10 because I multiplied 2 by 5. Once you have the POH, you're gonna use the formula of 14 minus this value. So calculating this, the pH is gonna be 11. Which of the following is the correct mathematical relationship to calculate pH of a strong acid? Again, a strong acid is gonna fully ionize, so whatever concentration I have here, I'm gonna have the same for H+. So therefore I can say pH is minus log of 0.10. The pH is not this value. Okay, here we go. 26. In pure water, some of the molecules ionize according to the equation, autoionization. The extent of the ionization increases with temperature. Again, yes, we learned this in class. When temperature increases, equilibrium move forward. More H plus and OH minus will be produced. Kw will be higher, but what remains the same idea is that the concentration of both will always remain the same. They will increase, but they will remain equal. So which of the following mathematical relationship gives the pOH of pure water? Okay, so if OH minus is gonna be equal to H3O plus, look, here's the answer, then definitely pOH is gonna be equal to pH minus always. These ideas remain the same. If I wanna calculate, I would say H3O plus or OH minus is a square root of Kw. Here, they used this formula. Question 27. Let's look at the diagram first. there's an H and a plus. So obviously that's the proton donor. That's the acid. Of course, that's the base because of the presence of the N. That's the conjugate acid, and that's the conjugate base. Okay. And the reaction is going in one direction. So they want us to think that this side is stronger than this side. It goes in one direction. So in the reaction, etc., Bronsted, so they're talking about this acts as a base. No. Okay, so it's very obvious. Next question. So here I have a graph of a pH decreasing as the temperature increase. Okay, as the temperature increase, Kw again increases, temperature increase, Kw increases, concentration of H plus and OH minus will always remain the same. pH and POH, not the same, I mean equal. pH and OH minus, pH and POH will always remain equal, but they will be higher. Okay, equal but higher. Now, so if H plus is higher, so these are equal but in some values. I don't want to confuse you, so I'm not going to write this. So in pure water, some of the molecules ionize according to the equation H plus. The extent of the ionization increases, correct? The graph above shows that the pH at different temperatures. Now, since pH is decreasing, since pH and POH are equal, then definitely POH is going to decrease if they are equal. Which of the following represents the... so they're looking at what's going to happen to the POH. POH and pH will always remain equal. So I'm going to start from the graph that starts from 7.2 and goes down just like the pH. So POH 7.2. This is showing a different start. This is showing a different start. And even here it's increasing. Here it shows that it remains the same. Here it's, so it's very simple. It is A. Moving on with the questions. So ammonia, it's a weak base. Here's the conjugate, here's the KB. Here's the weak ionization. This reaction between ammonia and water is represented above. A solution that is initially at 0.2 molar in NH3 has a pH of 11. Of course, it's basic. Which of the following correctly predicts pH of a solution with an initial concentration of 0.1? Well, if we started with a less concentration, the pH still gonna be basic, but less basic. Now I can do the fast way in calculating X if I do the IC table. Okay, but here they are not giving me the value, they're just comparing it. Now if that makes you comfortable, X here is OH minus, and it's a square root of KB times the initial concentration. You can just do this and choose the best choice. Now, or you can just read the answer. Now the answer is going to be even lower than 11.2. Let me give you the answer. 1.8 times 10 negative 5 times the concentration that I'm gonna use here. Now the answer is minus log answer. That's the POH. So it's gonna be 11.128. So the pH is 11.128. So first I calculated OH minus, then I got the POH by finding minus log OH minus, then I said 14 minus POH to get the pH. So anyway, it's gonna be less here, 11.28, so it's gonna be lower. So let's focus on these two options. Decreasing the initial concentration of NH3 increases the concentration of, no, that's not correct, because we're gonna get less OH minus, and OH minus is always equal to the amount of NH4 plus. So the pH is lower because the equilibrium concentration of OH minus now is gonna be less, X is gonna be less. So yes, that's the answer, B. Now, 10 milliliter of a solution of unknown acid HA is titrated with a 0.20 molar of NaOH. The reaction that occurs during the titration is represented by the following equation. Okay, so here we're looking at a titration of an acid with a base. Now, since the pH is above, not 7, now I know that we didn't take titration, but still we can read the question. So I still not sure about the information of HA because I didn't explain it in class. However, this is a weak acid because the pH at equivalence is not 7. Anyway, let's not focus on this. Which of the following is a conjugate acid-base pair? HA, A minus, OH minus, H2O. So the correct answer is D. See, the question is not even related to titration. Enough distilled water is added to 30 milliliter of a sample of a strong acid with a pH. So they are diluting the acid, so that the final pH of the diluted solution is 5.2. The volume of distilled water is added to the original concentration. Solution is closest to how much? So here they diluted the pH. So this is okay, so I had a 30 milliliter of a pH 4.22. Let's directly think about H plus. So pH equal minus log H plus, or H plus equals 10 to the power negative pH. So when I had a 30 milliliter solution, I'm always doing this formula. So times 10 to the power negative 4.20. So the final pH of the diluted solution is 5.2, which means the final concentration is 10 to the power negative 5.2. How much is the volume of distilled water added to the original concentration? So here I can find the value. So times 10 to the power five 0.2. So I found the concentration over here to be 300 milliliter. However, read the question carefully. How the volume of the water added. This is the total volume. Yani I have the 30 milliliter. Now the new volume is 300. So it means this is the amount of water that I added. So 300 minus 30, this is the water added. Next question. Again, autoionization of water, they lowered the temperature. So the Kw is gonna be less because Kw increases when the temperature increases. Kw decreases when the temperature decrease. always the concentration of OH minus and H3O plus remains equal. They vary, but they remain equal. pH and pOH, they're always equal, but they might increase or decrease. Now here they're talking about pKw. So pKw is opposite to Kw. So as Kw increase, pKw decrease. Or as Kw decrease, pKw increase. Okay, so based on this information, which of the following is correct for pure water at this temperature? So if I want to calculate pure water, I'm going to say H3O plus or OH minus is a square root of Kw because they are always equal. And I think this is the last question in the multiple choice section. The particle diagram above represents an aqueous solution of a weak monoprotic acid. The white circles represent H. This is H2O. This is H3O plus. This is an unionized acid. This is like HA. And this is like A minus. Okay. So, which of the following species that act as Bronsted Lowry base and its conjugate acid in that order solution? Okay. So let's see. I have HA that looks like this, gray and white. So I don't have gray here. Let me just here's gray. Okay, so gray and white plus H2O, it's gonna be this one, the black and two white. I don't have to show it to you, but we know what I'll do. That's the H2O. Now this is gonna produce A minus, which gonna look like just gray, and H3O plus, which is gonna be this black with 1, 2, 3. So acid, conjugate acid, base, conjugate acid. So they just want the pairs. No, H2O, OH minus. That's a tricky one. We don't have this over here. It's this one, H2O and H3O plus. That's the end of this first section of our revision question.